So today's topic is orthographic projection. Today we are going to study about the concept of projection, and then we are going to look into the details of orthographic projection as one of the important or popular methods of projection. But at the very onset, let us look at the motivation behind the introduction of this topic of orthographic projection in the field of engineering drawing. So when people started their journey with engineering drawing, when people realized that engineering drawing is going to be one of the most important tools for the advancement of technology and for the modernization of our lives, uh, they faced a major challenge in the initial days of implementation of this subject. So in one of the earlier classes, in one of the introductory classes, we have talked about this challenge, and the major challenge, the biggest roadblock in front of people dealing with engineering drawing in the initial days of implementation of this subject was how to represent a real life object, how to represent a real life object. Real life objects, as we all know, they are three-dimensional in nature. So whenever we are trying to represent a real life object through a technical drawing, we are doing this drawing either on a drawing sheet or on the board, which is a two-dimensional entity. So we are always faced with this challenge of representing three-dimensional objects on two-dimensional surface, or in other words, on planar regions. So how to do this? That was unknown to people dealing with engineering drawing in the early days of implementation of this subject. So as a solution to this problem, a French mathematician whose name was Gaspard Monge, he introduced this technique of orthographic projection as a solution of this problem of representing three-dimensional objects or real life objects on two-dimensional surfaces without losing out on any details regarding its shape and size. So that is the reason behind the introduction of this technique of orthographic projection, which is one of the most popular tools in the field of engineering drawing. So let us see this in the upcoming slide. So as you can see, the method of orthographic projection, this was introduced by a French mathematician, Gaspard Monge, to solve the problem of representing a three-dimensional object on a two-dimensional surface. So this is the problem that people wanted to solve. Representation of a three-dimensional object, representation of all details of a three-dimensional object on a two-dimensional surface or on a planar surface. This was one of the biggest challenges faced by people in the early days of implementation of engineering drawing. So many people tried to offer different kinds of solutions to this problem. French mathematician Gaspard Monge came up with the best possible solution, and the name of the method which he proposed, that is orthographic projection, which we are going to learn in detail in today's class. So this orthographic projection was a tool introduced by Gaspard Monge, which was able to solve this particular problem of representing three-dimensional objects on two-dimensional surfaces. Now, before learning the concept of orthographic projection, let us look at the concept of projection as a general topic. So let us try to understand what is projection, and let us try to understand some basic terminologies associated with projection. So in this slide, what you can see is there is an observer, which is this person. Then there is an object, a three-dimensional object with a very simple geometry. And then there is a plane which is located somewhere with respect to the object. Then you see that a number of imaginary lines are originating from the edges of the object. These are those imaginary lines, these blue colored lines that you can see. These are some imaginary lines which are originating from different points of this object and going and hitting this plane. So when this happens, that is when imaginary lines are drawn from different points on the contour of an object. Contour of an object is nothing but the collection of different edges of the object. So this object has several edges. There are millions of points on those edges. From each one of these points, if we draw imaginary lines like this, which are originating from different points of this object and going and hitting this plane, then we say that this object is projected on this plane. So this is how we can define the concept of projection. So let us give it a reading once more, whatever is written on this slide. If imaginary lines are drawn from different points on the edges of the object to meet a plane which is located somewhere with respect to the object, then we say that the object is being projected on that plane. So here we see a single plane and imaginary lines are connecting the object with that plane. So we say that this object that we can see here is being projected on this plane. Sometimes we can have multiple planes also. So let us go to one of the future slides and see a situation where the object is being projected on more than one plane. So please let me change the slides and go to one of the future slides. Yes, this is the appropriate slide. Here you see, this is the object. The observer may be situated somewhere with respect to the object. He may be here. He may be on this side of the object. He may be on the top of the object. But you see, from this object, three sets of projectors are emerging. So one set of projectors, which are represented by this set of lines. Projectors are nothing but these imaginary lines that we are talking about, which are originating from different points on the object and going and hitting a plane which is located somewhere with respect to the object. So here we see three different planes. So this is one plane, this is another plane, and this is yet another plane. So here you see one set of such imaginary lines are originating from the object and they are going and hitting plane number 1. So these are those imaginary lines which are originating from different points on the contour of the object and they are going and hitting plane number 1. So when this is happening, we are going to say that this object is being projected on this plane. Now, if you consider this set of imaginary lines, which are again originating from the same object, but going and hitting a different plane, then we will say that the same object is now being projected on this plane. Again, if you consider the remaining set of imaginary lines, which are these are also originating from the same object, but these lines are now going and hitting this plane. So now we are going to say that this same object is being projected on this plane. So this is how we can define the concept of projection. So let me go back to the earlier slide where a very simple geometry, where an object with a very simple geometry was being projected on a single plane. So let us go to that slide and understand the fundamental concepts related to projection. So this is the slide from where we started. So the concept of projection says that if imaginary lines are drawn from different points on the contour or edges of an object, and these lines go and hit a plane, then we will say that this object is being projected on the particular plane. Now, all these imaginary lines are hitting this plane at different points. See, all these imaginary lines which are originating from the object, they are hitting the plane at different points. Just give me 1 minute. See, this imaginary line, which is originating from some point of the object, is hitting the plane at this point. this imaginary line is hitting the plane at this point after originating from some other point of the object. This imaginary line, after originating from yet another point on the object, is going and hitting the plane at this point. And this imaginary line, after originating from one more point of the object, is going and hitting the plane at this point. Now, instead of just 4 imaginary lines, I can consider hundreds of such imaginary lines. All those lines will go and hit this plane at different points. Now, if I join these points in proper sequence, then I will get a figure on this plane, which is represented by this shaded region. Now, this figure, what is the importance of this figure? This figure will give us some details, if not all. This figure will give us some details about the shape and size of this three-dimensional object. And this figure is called as the projection of this object on this plane. And the plane is called as the plane of projection. So this is what you have to understand very thoroughly. So again, I am repeating, we have an object, we also have an observer who is looking at the object from some direction. Now, several imaginary lines are originating from the object. Several imaginary lines are originating from different points of the object, and they are going and hitting this plane. So when this happens, then we say that this object is being projected on this plane. Now, all these imaginary lines which are originating from the object and going and hitting this plane, all these imaginary lines are hitting this plane at various points. If you join those points in proper sequence, you will get a figure like this on this plane. This figure is called as the projection of the given object. This figure is called as the projection of this object on this plane. Instead of projection, sometimes we use the jargon projected view. Instead of projection, sometimes we use the jargon projected view. So this figure is called as the projection or projected view of this object on this particular plane. What is the importance of this projected view? This projected view will give us some details about the shape and size of this object. For example, if we want to know what is this dimension of the object, that we can extract from this projected view, from this part of the projected view. Again, if we want to know what is this dimension of the object, that also we can extract from this projected view. But if someone asks what is this dimension of the object, this we cannot extract from this projected view of the object on this plane. Okay, then for that we have to project this object on a different plane maybe. But this is the concept of projection or projected view of an object on a particular plane. The plane itself is called as the plane of projection. This POP that you see here, the full form of this POP is plane of projection. So the definition of plane of projection, you can see on this slide. The plane on which we are projecting the object, that plane is called as the plane of projection. And in order to project the object on this plane of projection, we have taken the help of several imaginary lines which are represented by these blue colored lines. These lines are called as the projectors. These lines are called as the projectors. So these projectors are basically the imaginary lines which are originating from the object and extending up to the plane of projection. And these lines allow us to obtain the projected view of the object on the plane of projection. These imaginary lines are called as the projectors. So projectors are basically connecting the object with its projected view on a particular plane of projection. Now, what is the physical significance of these projectors? What are these projectors actually representing? What is the physical significance of these projectors? Let us discuss. What is the physical significance of these projectors? What are these lines in blue actually representing? We are saying that these lines are originating from the object, going and hitting the plane of projection at different points. When you join those points in proper sequence, you are going to get the projected view of this object on this plane of projection. All that is fine. But these projectors are basically representing the light rays which are originating from the eyes of the observer. Light rays. The projectors are basically representing the rays of light which are originating from the eyes of the observer when he is looking at the object. These light rays are sweeping past the boundaries of the object and ultimately they are terminating on the plane of projection. In the process, you are able to project the object on the plane of projection and get the projected view, which is also called as the projection itself. That projected view will reveal some important information about the shape and size of this object. And finally, the location of the observer, the place from where the observer is looking at the object, that is called as the station point, or sometimes it is called as the center of projection. So these are some of the important terminologies which are associated with the concept of projection. So again, I am repeating whatever we have discussed related to the general concept of projection. We are yet to enter into the concept of orthographic projection, which is the topic for today's class. So it is very important for you to understand the general concept of projection in order to understand the concept of orthographic projection, which is just one of the types of projection. So the general concept of projection says that when imaginary lines like this are drawn from different points of an object, and these lines go and hit a plane which is located somewhere with respect to the object, then we say that this object is projected on this plane. Now, all these imaginary lines which are originating from the object and going and hitting this plane, all these imaginary lines are going to hit this plane at various points. For example, this line hits the plane at this circle point. This imaginary line hits the plane at this circle point. The third one hits the plane at this circle point, and the fourth one hits the plane at this circle point. Other than these four imaginary lines, if you consider several other imaginary lines also, then all those imaginary lines will also go and hit the plane at different other points. If we join all these points in proper sequence, then we will get a figure like this on this plane, and this figure will reveal some important information about the shape and size of this object. So this figure, which is obtained on this plane, this figure is called as the projection of the object on this plane, or the projected view of the object on this plane. The imaginary lines which are connecting the object with its projected view, these imaginary lines are called as the projectors. The projectors are nothing but the rays of light which are originating from the eyes of the observer, going past the object, and finally hitting the plane of projection. So that is the physical significance of the projectors. They represent the rays of light which are originating from the eyes of the observer, going past the object, and finally hitting the plane of projection. The location of the observer is called as the station point or center of projection, and the plane on which we are projecting the object, that plane is called as the plane of projection. So here POP means plane of projection. So that is all about the general concept of projection. Now let us take a look at the popular types of projection. So there are several types of projection, and the most popular ones are as follows. So we have a type of projection which is called as orthographic projection, which we are going to study in detail in today's class. Other than orthographic projection, there is another type of projection which is called as isometric projection. We are going to study isometric projection also in a slightly lesser detail compared to orthographic projection. Then we have certain other types of projection which are called as oblique projection and perspective projection. So these are the most popular types of projection. Now, Out of these 4 types of projection, whose names you can see on this slide, the second, third, and fourth types, they can be grouped into one category. Let me call this as category 1. And orthographic projection can be said to belong to a different category. Let me call that as category 2. So on some basis, we can do this segmentation of the different types of projection that we are seeing on the slide. So isometric projection, oblique projection, and perspective projection, they can be bucketed into one segment, whereas orthographic projection falls in a different segment. So what does this mean? This means that there must be some property which is common to isometric projection, oblique projection, and perspective projection, but that property is absent for orthographic projection. So what is that property? That property is very simple. When you are following any of these methods of projection, when you are following either isometric projection or oblique projection or perspective projection, one single projected view of the object on a single plane of projection, will reveal all the details about the shape and size of the object, or all dimensions of the object. Whenever we are projecting any object on a plane and obtaining the projected view of the object on that plane, our ultimate objective is to extract the details of shape and size of the object. So when you are following isometric projection, oblique projection, or perspective projection, any one of these methods, then you can fulfill your objective through a single projected view of the object on a single plane of projection. But if you are following the method of orthographic projection, then a single projected view will never give you all the details about the shape and size of the object. You will require at least 2 views. You will require at least 2 views. At least 2 views means at least 2 different projected views of the object on 2 different planes of projection in order to know. So at least 2 views, at least 2 different views of the object on 2 different planes of projection will be required to know all the details about the shape and size of the object. You cannot get all the details about the shape and size of the object from a single view if you are following orthographic projection. And this is the reason why orthographic projection is slightly different from the other 3 types of projection whose names you are seeing on this slide. So if you are following isometric projection, oblique projection, or perspective projection, a single projected view of the object on a single plane of projection will be revealing all the details about the shape and size of the object. But unfortunately, that is not possible when you are following the method of orthographic projection. So in orthographic projection, at least 2 projected views of the object are mandatory for revealing all the dimensions of the object or all details about the shape and size of the object. You cannot get all the details about the shape and size of the object from a single projected view if you are following the method of orthographic projection. You need at least 2 views. Sometimes you may need more than 2 views also for further clarification. So now I am erasing all this ink. You can always go through the recording later. And this PowerPoint presentation is already there with you in your WhatsApp group in the form of your study material. So you can give it a reading anytime later according to your free time. So whatever I have discussed over the last few minutes, that is clearly written on this slide. Out of the popularly used methods of projection, the method of orthographic projection is the only method that requires more than one projected view of the object for describing the shape and size of the object completely. But if you use isometric projection, oblique projection, or perspective projection, you can do this description of shape and size of the object completely with the help of a single view, single projected view of the object on a single plane of projection. This thing can be seen with the help of this illustration, which is there on the slide itself. So in this slide, you can see two different types of views. This view, which you see here, this is the isometric projection of the object. This is the isometric view of the object. So you see, this view can reveal all the details about the shape and size of the object. And this is just one view, which you are seeing. So when you are following the principles of isometric projection, the view of the object will look something like this, if this is the object. For other objects, the view will look slightly different, but the nature of the view will be similar to this, where all the details of the object, all details about the shape and size of the object can be extracted from a single view. So this is called as the isometric view of the object. This is the isometric view of the object. Whereas these views, which you see on the right hand side, how many are there? There are total 3 views. These views are called as the orthographic views. These are the views of the object obtained through the method of orthographic projection. These are the orthographic views. So how many views are there? Front view is one of the orthographic views. So this is the first view. Then we have something called as the top view. This is the second orthographic view. And then we have something called as the side view. This is the third orthographic view. So you see there are total 3 views, which are equivalent to this one isometric view. So we will talk about these orthographic views in more detail later on, going forward in this class. But for the time being, I just want you to acknowledge the fact that a single isometric view of the object can give you all the details regarding the shape and size of the object, whereas a single orthographic view will never give you all the details about the shape and size of the same object. So if you want to get all the details about the shape and size of an object through orthographic views, you have to obtain at least 2 orthographic views. Sometimes we go for 3 or 4 orthographic views also. But at least 2 orthographic views are a bare minimum if you want to extract all the information regarding the shape and size of the object from those orthographic views. Now, with this knowledge in the background, we will study the definition of orthographic projection. So now we are entering into the details of orthographic projection, and slowly things will become clear to us why in orthographic projection at least 2 views are required for complete description of shape and size of the object. Now, look at this illustration, which is given on this slide. So here also you can see the fundamental things. The observer is there. The same object has been taken as the example. We have the plane of projection, and with the help of the projectors, which are the blue colored lines, we are projecting this object on this plane of projection. And the resulting view is called as the projection or the projected view of the object on this particular plane of projection. Now you carefully observe the projectors. I would like you to very carefully observe the nature of the projectors. If you carefully observe the projectors, here you see only 4 of them, but I can draw even more. I can draw hundreds of them. But just for the sake of clarity, only 4 projectors have been included in this illustration. So just take a look at this collection of 4 projectors. So if you observe these projectors very carefully, you will find out 2 important characteristics about these projectors. The first important characteristic is the projectors are all parallel. All the projectors are parallel to one another. And the second important characteristic is each projector is perpendicular to the plane of projection. Each projector is perpendicular to the plane of projection. So when these two characteristics are satisfied by the collection of projectors, then the method of projection which is being followed, that is called as orthographic projection. This is the definition of orthographic projection. So if the method of projection has to be tagged as orthographic projection, then all the projectors have to be parallel, and each projector must make an angle of 90 degree with the plane of projection when it is intersecting the plane of projection. So when these two conditions are satisfied by the collection of projectors, then the method of projection which is being followed, that is called as orthographic projection. From the world of mathematics and geometry, we know that the term ortho has something to do with perpendicularity. So this perpendicularity comes from the fact that each and every projector is perpendicular to the plane of projection, from this part of the definition. So please take a look at the formal definition which is written in the slide. So if the projectors are parallel to one another, and if each and every projector is also perpendicular to the plane of projection, then the method of projection is called as orthographic projection. Let us go to the next slide and discuss more about this definition. Now, the station point or center of projection. What is station point or center of projection? As we have discussed earlier, the location of the observer is called as station point or center of projection. This we have discussed earlier, that the location of the observer is called as station point or center of projection in any method of projection. In orthographic projection, this station point or the location of the observer, this is assumed to be at a theoretically infinite distance from the object. Why? Let us try to convince ourselves why the observer needs to be situated at a theoretically infinite distance from the object in case of orthographic projection. Now, the opposite of infinite is finite. Now let us see what is the problem if the observer is situated at a finite distance from the object. If the distance between the observer and the object is a finite one, then what is the problem? Now, if the observer is situated at a finite distance from the object, then what will happen is, when the observer is viewing the object, the rays of light which are originating from his eyes, these rays of light are nothing but the projectors, as we have discussed earlier. The physical significance of the projectors is that the projectors are nothing but the rays of light which are originating from the eyes of the observer, going past the object and finally hitting the plane of projection. That is the physical significance of the projectors. That is the real life implication of the projectors. That is the real life meaning of the projectors. So when the observer is viewing the object from a finite distance, then these projectors or rays of light originating from the eyes of the observer can be either convergent in nature or they can be divergent in nature. These are the only two possible options. So convergent light rays look like this. This is convergent light rays. And divergent light rays look like this. All of you have studied this a lot of times in physics. This is how divergent light rays appears. Now, whether the light rays will be convergent or divergent, the light rays are originating from the eye of the observer in both the cases. Now, whether the light rays will be convergent or divergent, that depends on the size of the object which the observer is looking at. So if the observer is looking at a very small object, then the light rays coming from his eyes will be convergent in nature. And if the observer is looking at a very large object, at least larger than his eyes, then the light rays which are originating from the eyes of the observer, they will be divergent in nature. In none of these two cases are the projectors or light rays parallel. But according to the definition of orthographic projection, the projectors or light rays originating from the eyes of the observer going past the object and hitting the plane of projection have to be like this. That is, all the projectors have to be parallel. But if the observer is looking at the object from a finite distance, the light rays originating from his eyes will be either convergent in nature if the object being looked at is a small object, or the projectors will be divergent in nature if the object which the observer is looking at is a large object. But in none of these two cases, the projectors will be parallel. So the definition of orthographic projection will be violated if the observer is situated at a finite distance from the object. That is why we have to push the observer to a theoretically infinite distance from the object. So if the observer is situated at a theoretically infinite distance from the object, then what will happen is the length of these projectors will become infinity in both the cases of convergent light rays or divergent light rays. Then over a very small portion of their total length, we can approximately consider this collection of projectors to be parallel and satisfy the definition of orthographic projection, which says that all the projectors have to be parallel and also perpendicular to the plane of projection. So since the definition of orthographic projection wants the projectors to be parallel, therefore, in order to make the projectors forcefully parallel, we have to shift the observer to a theoretically infinite distance away from the object, so that the length of the projectors become infinity, and over a very small length of that infinitely long projector, we can approximately consider a collection of them to be parallel, thereby satisfying the definition of orthographic projection. Now, why do we want parallel projectors? Why do we don't want convergent or divergent projectors? This is because there is a problem with convergent projectors as well as divergent projectors. You see, here the projectors are all parallel. But if these projectors were convergent, then the problem would have been that the projected view would have been smaller than the object. The size of the projected view would have been smaller than the object if these projectors were convergent instead of parallel. And if the projectors were divergent, in that case, we would have faced the opposite problem. In that case, the projected view of the object would have been bigger than the actual object. So we don't want any of these two situations to happen. We want the size of the projected view to be exactly equal to the size of the original object, because from the projected view, we want to be able to extract the original dimensions of the object. That is why we are drawing the projected view on the plane of projection, so that we are able to extract the original dimensions of the object by looking at the projected view. So for that to happen, first the projected view has to be equal in size to the object, and for that to happen, the projectors have to be parallel, and that can happen only if the observer is situated at a theoretically infinite distance from the object. If the observer is situated at a finite distance from the object, then the projectors will be either convergent or divergent. In the first case, when the projectors are convergent, that is when the observer is looking at a small object from a finite distance, in that case, the projectors will be convergent, and that will make the size of the projected view smaller than the object. Again, if the observer is looking at a large object, large means larger than his eyes, from a finite distance, then the projectors will be divergent in nature, and that will make the projected view bigger than the actual object. But we want the projected view to be equal to the object in terms of size. So if the size of the projected view has to agree with the size of the actual object, then the projectors have to be parallel. And projectors can be made approximately parallel if the observer is situated at a theoretically infinite distance from the object. That is why in orthographic projection, one of the key points to remember is the station point or center of projection is at an infinite distance from the object. If that happens, then the size of the projected view will be equal to the actual dimensions of the object. The dimensions of the object on the projected view will be equal to the actual dimensions of the object. Okay. So that's all about the definition of orthographic projection. So these are some important points that you have to remember, that for orthographic projection, all the projectors have to be parallel amongst themselves, and each projector must hit the plane of projection at an angle of 90 degrees. So all the projectors have to be parallel, and not only that, each projector has to be perpendicular to the plane of projection. The projectors need to be parallel so that the size of the projected view and the size of the object are consistent with one another. And in order to make the projectors parallel, we have to shift the observer to a location which is at a theoretically infinite distance from the object. So station point or center of projection, which is nothing but the location of the observer, in case of orthographic projection, is at a theoretically infinite distance from the object. Now we have already discussed that in orthographic projection, more than one view of the object is required for extracting all the details about the shape and size of the object. So let us talk about all those different kinds of orthographic views and the planes of projection which contain those orthographic views. So for that, let us move to one of the future slides. So let us look at this slide. Let me erase all the ink from this slide. The content of this slide you will see later. First, let me write something here. There can be different types of orthographic views. I am writing their names first. First, you take a look at the names of the different possible orthographic views and also the planes of projection which contain these views. So there can be 4 types of orthographic views. One of them is called as the front view. So from the name itself, you can understand that this is the view of the object which is obtained when the observer is assumed to be looking at the object from the front of the object. The front view of the object is also called by the name elevation. Elevation is an alternative name of the front view. Other than front view, we also have another type of view which is called as top view. Top view of the object, as the name suggests, is the view of the object which is obtained when the observer is looking at the object from the top of the object. The top view of the object is also referred to as the plan view. Then we have the side view. So side view of the object is the view which is obtained by looking at the object from the side. Now an object can have two sides, left hand side and right hand side. So a person can look at the object from its left hand side and get the left hand side view. Similarly, the same person can look at the same object from its right hand side and get another type of side view, which is called as the right hand side view. So these are the different possible orthographic views that you can come across: front view, top view, side view. Then under side view, we can have two variants: left hand side view and right hand side view. Each of these views will reveal some details about the shape and size of the object. Now, since we have 4 different types of views, we should also have 4 different types of planes of projection which will contain these views. Which plane will contain which view, that we will see very soon. So now let us go to the discussion on planes of projection. Planes of projection. So in orthographic projection, we have 3 mutually perpendicular planes of projection. We have 3 mutually perpendicular planes of projection. Out of those 3 planes, two planes you can see in this diagram itself. So in this diagram, you can see that there is one plane here. This is one plane. Now from the orientation of this plane, you can call this plane as the vertical plane. If this is the vertical plane, then this becomes the horizontal plane. So these are the first two planes of projection. They are mutually perpendicular. Vertical plane is perpendicular to the horizontal plane and vice versa. So first we have the vertical plane. We will not use the full form all the time. We will be using the short form. So vertical plane can be abbreviated as VP. Vertical plane is a plane whose configuration is vertical, as simple as that. The orientation of this plane is vertical. Then we have another plane which is called as horizontal plane. So the short form of horizontal plane is HP. So vertical plane and horizontal plane you can directly see in this diagram. Now there is another plane, another possible plane which can be shown like this. Please pardon my drawing, it's very bad. So this plane that you are seeing here, this is a plane which is at 90 degree to the vertical plane, and this is also at 90 degree with the horizontal plane. So this is a plane which is perpendicular to both the vertical plane and the horizontal plane. This plane, this third plane, which I have drawn just now, this is called as the profile plane. This is called as the profile plane. So the short form of profile plane will be PP. Now I can draw one profile plane at this location. Similarly, I can draw another profile plane somewhere here. This can be tagged as another profile plane. So you see there are 4 planes of projection and there are 4 orthographic views. So it is quite obvious that each one of these planes of projection will contain one orthographic view. So vertical plane will contain one of these views. Horizontal plane will contain another view out of these 4. And the 2 profile planes that I have drawn will contain the 2 remaining views, one each. So let us see which view, which orthographic view will be projected on which plane of projection and why. So let us study that in detail. So for that, just let me change the ink color. Let me use a different ink color. So all of you are now requested to follow the second diagram. What is my pointer? Yes. Please follow this diagram. So here you can see a 3-dimensional object. So this is the object. And for the time being, just satisfy yourself with 3 planes. This is one plane. This is another plane. The planes are not connected in this figure, but if stretched, the planes will eventually meet. And all these 3 planes are 3 mutually perpendicular planes. So if you consider plane 1, it is perpendicular to plane 2 and 3, both. If you consider plane 2, it is perpendicular to both planes 1 and 3. If you consider only plane 3, it is perpendicular to both the planes 1 and 2. Now, out of these planes, which is the vertical plane? So if you brush up your definition of vertical, then this plane 1 becomes the vertical plane. And again, if you brush up your definition of horizontal, then plane 2 becomes your horizontal plane. And plane 3 becomes one of the 2 possible profile planes. Now, suppose you are looking at the object from the front. That is, you are looking at the object along the direction of this arrow from a theoretically infinite distance. So station point or location of the observer is at infinity as per the definition of orthographic projection. So when you are looking at the object from the front, you are basically trying to draw the front view of the object. So in order to get the front view of the object, you have to look at the object along the direction of this arrow, this one. So when you are looking at the object in this direction, then these lines are the set of parallel projectors. Now this set of parallel projectors will hit the vertical plane perpendicularly out of the three planes which you can see in this figure. Therefore, the front view of the object will be captured on the vertical plane. So how will you get the front view of the object? You have to imagine that you are looking at the object from the front from a theoretically infinite distance. So this arrow represents the direction of viewing. So when you are looking at the object from the front, then the projectors will be represented by this set of imaginary lines. These are the light rays which are coming from your eyes, going past the object and finally hitting this plane perpendicularly. So all these projectors are hitting the vertical plane perpendicularly at different points. If you join those points in proper sequence, you will get a figure like this on the vertical plane, which is nothing but the front view of the object. So front view of the object is projected on which plane? The front view of the object is projected on the vertical plane. Now, after obtaining the front view, suppose I want to obtain the top view. So whatever I have got, let me make a note of that. So front view of the object, as we have discussed, is projected on the vertical plane of projection. Why? This is because when you are looking at the object from the front, the relevant set of projectors will hit the vertical plane perpendicularly. These projectors, which are shown by yellow with a tick mark on each one of these projectors will neither hit the horizontal plane perpendicularly, nor will they hit the profile plane perpendicularly when you are looking at the object from the front. So the projectors which come into existence when you are looking at the object from the front, these projectors will hit only the vertical plane perpendicularly. And that is why you will get the front view of the object on the vertical plane. So since the vertical plane contains the front view of the object, the vertical plane is also called as the frontal plane. Since the vertical plane contains the front view of the object, because of that reason, sometimes the vertical plane is also called as the frontal plane. Now, after obtaining the front view of the object, let us try to get the top view of the object. Now, let us try to obtain the top view of the object. So when you are trying to obtain the top view of the object, you are looking at the object along the direction of this arrow from a theoretically infinite distance. So now the projectors are no longer these ones. These ones are no longer the projectors when you are looking from the top. When you are looking from the top, the projectors are represented by this set of lines. These are the light rays which are coming from your eyes, going past the object. And this set of parallel projectors will hit which plane perpendicularly? They will hit the horizontal plane perpendicularly. So the top view of the object is projected on the horizontal plane. And this top view can be drawn by joining all the points in proper sequence where the projectors are hitting the horizontal plane perpendicularly. So this is the top view of the object, which is obtained on the horizontal plane of projection. So the horizontal plane of projection is the plane of projection which contains the top view of the object. Sorry, the top view of the object is projected on the horizontal plane. Let me write it the other way around. That will make sense. So horizontal plane will contain the top view of the object, vertical plane will contain the front view of the object. The reason is very simple. When you look at the object from the top, then the projectors are the green colored lines. And these green colored projectors are having such a direction that they will go and hit the horizontal plane of projection perpendicularly. So the top view of the object will be captured on the horizontal plane of projection. When you are looking at the object from the front, then the projectors are represented by the yellow lines. This set of projectors will hit the vertical plane perpendicularly. That is why the front view of the object is projected on the vertical plane. Now let us see what will happen if we try to get the side view of the object. So for the time being, let us be content only with the left hand side view. We can extend this discussion for the right hand side view also. So for left hand side view, let me use a different color. Let me use this color. So now you suppose that you are looking at the object from the left hand side. Okay, I was searching for my pointer. So when you are looking at the object from the left hand side, this is your direction of viewing, and you are viewing the object along this direction from a theoretically infinite distance. So now your projectors are represented by this set of lines. Now your projectors are represented by this set of lines. These are the projectors which come into existence when you are looking at the object from the left hand side of the object. That is along the direction of this arrow. So this set of projectors represented by the light blue colored lines, this set of projectors are having such a direction that they will go and hit the profile plane perpendicularly. That is why the left hand side view of the object is being captured on the profile plane. So the side view of the object is always captured on a plane of projection which is called as the profile plane. So profile plane will contain the side view of the object. So you can see two profile planes in the first picture. If you look at the upper picture, you can see two profile planes. This one will contain the left hand side view. The other profile plane will contain the other side view, which is the right hand side view. So if you look at the object from this direction, then the projectors will be like this. And this group of parallel projectors will hit this profile plane at an angle of 90 degree, which is why the right hand side view of the object will be captured on this profile plane. So now we have learned about the different planes of projection and which plane contains which orthographic view and why. So let us see the summary of this discussion in one of the future slides. Let me deviate from this slide. So in this slide, you can see the summary of the discussion that we have just now carried out. So here you can see a table consisting of two columns. In the left column, you can see the names of the planes of projection. In the right column, you can see the names of the orthographic views which are captured in those planes of projection. So just have a look at this table. Before I go over to the next topic. Now you come back to this slide once. Here you can see different types of orthographic, different types of projected views. So let me change the ink color first. Let me use this color. So this orthographic view, this projected view, this is called as isometric view. This is not called as orthographic view. This is called as isometric view. So what is the characteristic of the isometric view? This view has been drawn following the principles of isometric projection. And the other views which you see here, these views are called as the orthographic views. These views are called as the orthographic views. These views are called as the orthographic views of the same object. So when you look at the object from the front, this is the front direction of the object represented by this green colored arrow. When you look at this object from the front, you will be able to see this surface. So the front view of the object will consist only of this surface. So that is why the front view of the object is like this. So this L-shaped surface is nothing but the shaded one. Now, this object is a three-dimensional object. So let us give some names to the different dimensions of the object. So let us say that this dimension of the object, this one, let us say that this is the length of the object. Let us say that this dimension of the object is the thickness. And let us say that this dimension of the object, this one, let us call it as the height of the object. Now you look at the front view. In the front view, can you see length, height, thickness, all the dimensions? The answer is no. In the front view, you can get the thickness of the object. From the front view, you can get the thickness of the object, and what you can get, that is called as the height of the object. The front view will give you the height, the front view will give you the thickness, but the front view will fail to give you the length. So one of the dimensions of the object is missing in the front view, and that is length. Length is missing in the front view. That is why one orthographic view is never sufficient to reveal all the dimensions of the object. But one isometric view can reveal all the dimensions of the object. So you can see length, height, and thickness, all the three sets of dimensions of the object through a single isometric view. That is the characteristic of an isometric view. A single view can tell you the entire picture. A single view can show you the entire picture. You can extract all details about the shape and size of the object from the isometric view, which is a single view. But when you try to do the same thing, when you try to extract all the details about the shape and size of the object from a single orthographic view, you will always fail. And that has been tested for the front view. Now let us test the same thing for the top view also. So when you are trying to obtain the top view of the object, you have to look along the direction of the red arrow. So the top view of the object will be obtained on looking at the object from a different direction, which is the top of the object. So you can obtain the top view of the object if you look along this direction. So when you look at the object along this direction, you will see this surface and you will see this surface. So you see this part of the top view is representing the top view of this surface, and this part of the top view is representing the top view of this surface. So why the top view is looking like this, I have explained that. Now you see from the top view, can you extract length, height, thickness, all the three? Again, the answer is no. From the top view, what you can get is this dimension, which is nothing but this one. This is what? This is the length. So from the top view, we can get the length, which was missing in the front view. And what we are getting for the second time, that is nothing but the thickness. This is the thickness. But from the top view, you cannot tell anything about the height axis. So all the height related features, their dimensions cannot be extracted from the top view. So you cannot tell what is the length of this edge. You cannot tell what is the length of this edge, because these are parallel to the height axis. So if you have only top view, you will miss out on the height. If you have only front view, you will miss out on the length. But if you have front view plus top view together, then you will get length, height, thickness, everything. Length you will get from the top view only, height you will get from the front view only, and thickness you will get in both the views. So front view alone is not sufficient for complete description of shape and size of the object. Top view alone is also not sufficient for complete description of shape and size of the object. But front view and top view taken together is giving you enough information about the shape and size of the object. You can check this for the side view also. If you take a look at the object from the side, that is along this direction, then you will see this surface and this surface. So these two surfaces of the object will be visible from the side. So these two surfaces will be part of side view. So you look at the side view, this portion of the side view, this is representing the side view of this surface, and this portion of the side view, this is representing the side view of this surface. So from the side view, you are getting out of length, height, and thickness, you are getting the height. This is the height. And you are getting the length. In the side view, the thickness is missing. So again, side view is not sufficient, front view is not sufficient, but if you work with the combination of these two views, then you have all the information, length, height, thickness, everything. Okay, so that is why in orthographic projection, you always need at least two views in order to describe the shape and size of the object completely. One view is never sufficient for serving this purpose. Each orthographic view will contain only two out of the three sets of dimensions of the three-dimensional object. So if you want to get the details of all the three sets of dimensions, you have to look at least two different orthographic views. Sometimes for further clarification, we can go for three views or all the four views. Okay. Now, in this slide, we are going to understand a very, very important thing. See, when we started off our discussion on orthographic projection, we have mentioned categorically that this method was introduced to solve the problem of representing three-dimensional objects on two-dimensional surfaces. This method of orthographic projection was introduced in order to solve the problem of representing all the details about the shape and size of three-dimensional objects on two-dimensional surfaces. Now the question is, based on whatever we have learned till now, can we say that this problem has been solved already, or we need to do something more? The answer is, indeed, we need to learn something more in order to get this problem completely solved. See, here we can see two planes of projection out of the three. We can understand this concept using two planes of projection. We can understand this concept using three planes of projection also. But for the sake of simplicity, here in this slide, I have included only two planes of projection. So you look at their names. We have the vertical plane of projection. So front view of the object will be captured on this plane. Then we have the horizontal plane of projection. The top view of the object will be captured on the horizontal plane of projection. So this information all of us know. Now, front view will give you only two out of the three sets of dimensions. Front view will give you maybe thickness and height. Length will be missing. And top view will give you length and thickness. Height related information will be missing. So when we have both front view and top view together, then we have the information about length, height, thickness, everything. Fine. But you see, this vertical plane, this is a 2D region, this is a two-dimensional entity. The horizontal plane is also a two-dimensional entity. But if I allow the vertical plane and horizontal plane to remain like this, then this combo, this combination, is it a two-dimensional entity? The answer is no. If I draw the vertical plane like this and place the front view here, and if I draw the horizontal plane like this and place the top view here, can I say that all the details of the three-dimensional object have been represented on a two-dimensional surface? The answer is a big no. Why? This is because the vertical plane is two-dimensional on its own. The horizontal plane on a standalone basis is two-dimensional. But when I'm working with these two planes in this kind of orientation, this combination is still three-dimensional. This combination is three-dimensional. Vertical plane is two-dimensional, horizontal plane is two-dimensional, but the combination, that is still three-dimensional. But my target is to bring all the details about the shape and size of the object on a single two-dimensional region. In other words, I want to bring all the views into the same plane. I want to bring all the views into the same plane. So how can that be done? That can be done if you rotate the vertical plane and align it with the horizontal plane like this. Or if you rotate the horizontal plane and align it with the vertical plane like this. In both cases, one of the planes of projection is being rotated through an angle of 90 degree because that is the initial angle between the two planes in their initial positions. So the rule says that vertical plane cannot be rotated. Why am I interested in rotating one of the planes? This is because I want to bring all the views into the same plane. Because my target is to represent all details of the three-dimensional object on the same plane, on a single two-dimensional surface. That is the objective with which I started off in my journey. So in order to bring all the details of the three-dimensional object on the same plane, on the same two-dimensional surface, I have to rotate either the vertical plane and get it aligned with the horizontal plane, or I have to rotate the horizontal plane and get it aligned with the vertical plane. So rule says that vertical plane cannot be rotated. This is just a convention. Vertical plane is assumed to be the drawing sheet. Vertical plane is assumed to be the drawing sheet. So vertical plane cannot be rotated. Everything else can be rotated. So you can rotate the horizontal plane if required. If required, you can also rotate the profile plane. Profile plane I have not considered here. I will consider it later on. So if you rotate the horizontal plane, there are two possible directions in which the horizontal plane can rotate. You can rotate the horizontal plane in the upward direction. You can rotate the horizontal plane in the downward direction also. If you rotate the horizontal plane in the upward direction, after the rotation is complete, the top view and front view will overlap with each other. So what I will do is, I will rotate the horizontal plane in the downward direction. So after that rotation is complete, this will be the new position of the horizontal plane. So what we will have is the line of intersection, which is called as the reference line. This line xy, which is the line of intersection of the two planes. This line, this is called as the reference line. So after the horizontal plane has been rotated through an angle of 90 degree, we will have the vertical plane sitting above the horizontal plane, sitting above the reference line, and horizontal plane will be sitting below the reference line. Horizontal plane you see is sitting below the reference line after the rotation is complete, and vertical plane from the very beginning, it was sitting above the reference line. So this situation that you are seeing here, is the situation after rotation of the horizontal plane. After rotation of the horizontal plane. So after rotation of the horizontal plane, it will come and lie below the vertical plane with the top view in it. So you see front view is above the line xy because this is the region occupied by the vertical plane. And top view will lie below the line xy because this is the region which is occupied by the horizontal plane after its rotation. And why has the rotation been carried out? This is because I have tried to bring all the views into the same plane because my objective was to represent all the details of the three-dimensional object on a single plane or on a single two-dimensional surface. That is why at the end, we are performing a rotation of some of the planes of projection to bring all the views into the same plane, which is same as the vertical plane. Now, in this entire discussion, something that I have mentioned regarding the direction of rotation, when we chose one of the two available directions, I have said that if you choose the other direction, there will be a overlapping of the views after rotation. But that is not exactly what the rule says. So what is exactly the rule regarding direction of rotation that we will see going forward. For the time being, you can assume that vertical plane was rotated in the downward direction because had it been rotated in the upward direction, after the rotation, the location of the horizontal plane would have been such that front view and top view would have overlapped with each other, and it would have been difficult to differentiate between the two views. That is why we have brought the horizontal plane downwards, and the consequence of that is this figure that you see. Okay, so we have covered the majority of this chapter, but still one major chunk of this chapter is left. So in the remaining time, I hope to complete that chunk also. So please give me some time to have some water, and then we will talk about the remaining topic, which is systems of projection. So I am not going through the things which are there on the slide. I am not allowing you to read the points which are written on the slide. You can do it later, because this PowerPoint presentation will be there with you throughout the semester. It is there in your WhatsApp group. The slides are there. So you can take a look at the slides anytime according to your convenience. The purpose of this class is the explanation of the concepts, so that when we do the drawing sheet in tomorrow's class for AIML Group A, you can understand and relate the problems that will be solved with the theoretical concepts. That is the sole purpose of this online class. So now we are going to talk about a very important topic related to orthographic projection, and the name of the topic is systems of projection. Now there are two different approaches following which you can solve problems on orthographic projection. You can draw front view, top view, left hand side view, right hand side view of an object following two different approaches. And these approaches are called as systems of projection. So the first system of projection is called as first angle system of projection. The other system of projection is called as third angle system. The other system of projection is called as third angle system. First angle system and third angle system, these are the two systems of projection. Now we will slowly understand the definition of these two systems of projection. We will see what is the similarity in these two systems and what is the dissimilarity. But let us start understanding the concepts from a fundamental point. So you look at this picture. I request all of you to look at this picture. Here you see this part of the red colored plane is the vertical plane, and this is the horizontal plane. I think it is already written. See, this is the horizontal plane and this is the vertical plane. Now, in whatever we have discussed till now, we have always drawn only this much of the vertical plane. We restricted the vertical plane only to one side of the reference line. What is the reference line? Reference line is the line of intersection of two planes of projection. So here the two planes of projection are vertical plane and horizontal plane. Their line of intersection is this line. This line is represented by x, y, and this line of intersection of the two planes of projection is represented by x, y, and it is called as reference line. This is called as the reference line. This is called as the reference line. Now, till now, we have dealt with only this shaded part of the vertical plane and only this part of the horizontal plane. Till now, we have dealt with only this much of the horizontal plane, only the shaded part of the horizontal plane and the shaded part of the vertical plane. That is, we have dealt with a situation like this, where vertical plane was restricted to only this much and horizontal plane was restricted to only this much. Now, if I extend both these planes beyond their line of intersection, if I extend the horizontal plane to this side also, and if I extend the vertical plane to this side of the reference line, then we are getting four different quadrants, which you can see here. This is the first quadrant, this is the second quadrant, this is the third quadrant, this is the fourth quadrant. I think I have messed up with this slide. in order to make you understand the things. So what I will do is I will quickly go to a blank screen. I will quickly go to a blank screen and try to explain. See, till now, I have to change the ink color in that case. So which ink color should I choose? Yellow, the brightest one. Till now, we have dealt with only this part of the vertical plane and only this part of the horizontal plane. Right? Now imagine that you are extending the vertical plane to the other side of the reference line. Reference line is the line of intersection of the two planes. So I am extending the vertical plane to the other side of the reference line. Similarly, I am extending the horizontal plane also to the other side of the reference line. So horizontal plane is no longer restricted to only this, but it is now expanding to this also. Similarly, earlier we considered only this part of the vertical plane. Now we are expanding the vertical plane to this side of the reference line also. So when I am doing this, when I am extending the vertical plane and horizontal plane beyond their line of intersection, then I am ending up with four quadrants. Extension of the planes of projection beyond their line of intersection is giving rise to four quadrants. What type of quadrant? These type of quadrants are called as three-dimensional quadrants. The quadrants which you have seen in your graph paper, they are two-dimensional quadrants, but these are three-dimensional quadrants. So let me label the quadrants. This is the first quadrant, which was there from the very onset when we started discussing this chapter. Every time we have drawn the vertical plane and horizontal plane, this first quadrant was always there. Now, the moment we have extended the horizontal plane and the vertical plane beyond their line of intersection, we have got three additional quadrants, which are nothing but the second quadrant, which is here, the third quadrant, which is here, and the fourth quadrant, which is here. Now, what is the use of these quadrants? These quadrants will be used for positioning the object, whose projected views we will try to draw on suitable planes of projection. So we can position the object in the first quadrant and then start obtaining the projected views on the suitable planes. We can position the object in the second quadrant and then do everything else. We can start by placing the object in the third quadrant. We can also start by placing the object in the fourth quadrant. Now, if we are placing the object in the first quadrant, how will you describe the position? How will you describe the position of the object? That needs to be understood. So if you are placing the object in the first quadrant, anywhere in the first quadrant, you are basically placing the object towards the front of VP and above HP. So you can say that the object is some distance in front of vertical plane and some distance above horizontal plane. This is how you can describe the position of the object if it is in the first quadrant. Now, if it is in the second quadrant, everything is gone. Quickly, I will get back things that I have lost. Vertical plane, horizontal plane. I'm extending the horizontal plane to this side of the reference line also. This is the reference line, line of intersection of the two planes. Similarly, I am extending the vertical plane to the other side of the reference line. So this becomes your first quadrant, this becomes your second quadrant, this becomes your third quadrant, this becomes your fourth quadrant. Fine. So if the object is in the first quadrant, for quadrant I am writing just Q. All these things are there in a slide, but still it is better to write. If the object is in the first quadrant, we can say that the object is in front of the vertical plane and above the horizontal plane. So object is in front of vertical plane, above the horizontal plane, if it is in the first quadrant. If I am now shifting the position of the object to the second quadrant, suppose the object is now in the second quadrant, how can you describe its position? The second quadrant is towards the back side of the vertical plane, but it is still above the horizontal plane. So I will say the object is some distance behind the vertical plane, but it is still above the horizontal plane. This is how you can describe the position of the object if it is in the second quadrant. Now, if the object is in the third quadrant, how can you describe its position? It is still behind VP, but now it is below HP. So this is how you can describe the position of the object if it is in the third quadrant. If the object is in the fourth quadrant, then the object is now back to the front side of vertical plane, but it is still below the horizontal plane. So this is how you can describe the positions of the object depending on whether it is in the first quadrant or second quadrant or third quadrant or fourth quadrant. Now, if the object is in the first quadrant, if you are assuming the object to be located in the first quadrant and then drawing the projections on the different planes, then the system of projection which you are following, that is called as the first angle system of projection. And if you are starting with the assumption that the object is located in the third quadrant, then the system of projection which you are following, that is called as the third angle system of projection. This is how we can define the two systems of projection. If you remember, in one of the earlier slides, I had written the two systems of projection are called as first angle system of projection and third angle system of projection. The first angle system of projection is that system of orthographic projection where in the initial stage of our work, we start with an assumption that the object is located in the first quadrant, that is in front of VP and above HP. If we start with a different assumption, that is the object is located in the third quadrant, that is behind VP and below HP, then whatever work follows, that falls under the third angle system of projection. Now the question is, what will be the difference in terms of the output that we get? What will be the difference in terms of the output that we get when we perform our work in the first angle system and when we perform our work in the third angle system? What will be the difference? Will the nature of the views differ? Will the front view in the third angle system differ from the front view of the object in the first angle system? Will the top view of the object in the two systems be different? Will the left hand side view of the object in the two systems look different? Will the right hand side view of the object in the two systems look different? The answer is no. There will be no difference in the appearance of the views, in the nature of the views. There will be no difference in terms of the nature of the views as long as the object remains the same. Again, I have lost the blank screen, but I don't need it. There will be no difference in the nature of the views, but the relative positioning of the views, that will be different. Where the views are positioned with respect to one another in the final solution, that will be different in the two systems. So let us understand this with the help of a example. So let us go to one of the future slides. Look at this slide. Here you see the isometric view of an object. Let me change the ink color. We don't have much time left, so I have to go a little bit faster. But still, if you don't understand anything, you can always unmute yourselves and ask. This is the isometric view of an object. So if you look at this isometric view and try to construct its front view, this is how the front view will look like. And this is also how the front view will look like. So in the front view of the object, when you are looking from the front, you will see this surface, you will see these two surfaces, and that is exactly what you are seeing here. So this is the front view of the object, this is the front view of the object. Now you see, all this work has been prepared according to the first angle system of projection by assuming the object to be located in the first quadrant. And all this work has been done by assuming the same object to be located in the third quadrant. So this is the output of third angle system of projection. So when you are doing the task of obtaining the orthographic views of the object following the first angle system, whatever front view you are getting the same front view in the third angle system also. So changing the position of the object from the first quadrant to the third quadrant is not going to affect the nature of the views. Keep it in your mind, as long as the object remains the same. If you change the object, then many things can happen. But as long as you keep the object same, you see in both the works, the isometric view of the object looks exactly the same. This is the isometric view here, and this is the isometric view here. In both cases, the isometric view is the one and the same. And that is why in both the cases, we are getting a similar front view. Now, if you look at the top view, if you look at the object from the top, what will you see? This surface, and this surface. So this is the top view. Compare it with the top view obtained according to the third angle system. Is there any difference? The answer is no. So again, we are getting evidence which tells us that there will be no difference in the nature of the views, irrespective of whether you perform it following the first angle system or whether you draw the view following the third angle system. At least the front view and top view is acting as enough evidence to this information. Let us check this for left-hand side view and right-hand side view also. So if this is the front of the object, this becomes the left-hand side and this becomes the right-hand side. So when you look at the object from the left-hand side, this is what you see. This is what you see. So this is the left-hand side view of the object in the first angle system. And this is the left-hand side view of the object in the third angle system. Compare the two views, there is no difference. Now, if you look at the object from the right-hand side, imagine that you are looking at the object from the right-hand side. So you will see this surface and this one. So this is the right-hand side view of the object in the first angle system. Compare it with the right-hand side view of the object in the third angle system, there is no difference. So there is absolutely no difference as far as the nature of the views are concerned in first angle system and in third angle system. So where is the difference lying? That answer you will also get from this slide only. That answer is there in this slide itself. The difference lies in the relative positioning of the views. The difference in the output of these two systems of projection. The difference lies in the relative placement or the relative positioning of the views. Please study the relative positioning of the views in the first angle system. Study it from here. We have front view somewhere, and below the front view, we have the top view. You see, below the front view, we have the top view. And on the right-hand side of the front view, we have the other side view, that is the left-hand side view. And on the left-hand side of the front view, we have the other side view, that is the right-hand side view. So this is the relative positioning of the views in the first angle system. Why are we having this kind of relative positioning of the views in the first angle system? That I will explain just now. But first, let us appreciate the result. Then we will do the deduction. So this is how the views are positioned with respect to one another in the first angle system. In the third angle system, this relative positioning of views is different. So here you see top view is lying above front view. In the first angle system, front view was lying above top view. But in the third angle system, top view is lying above front view. Right? That is one difference. Another difference is on the two sides of the front view, we have the two side views. So on the right hand side of the front view, sorry, one mistake I had made earlier. This is right hand side view and this is left hand side view. Why? This is because if you look at the object from the right hand side, you will see this surface, which is this one, and you will see this small surface, which is at one corner. So this is definitely the right hand side view. From the left hand side, you will see the reverse view. So this is left hand side view, this is right hand side view. So you see in the third angle system, on the right hand side of the front view, you have the right hand side view. And on the left hand side of the front view, you have the left hand side view, which was not the case in case of first angle system. In the first angle system, on the right hand side of the front view, we were having the left hand side view, and right hand side view was located to the left hand side of the front view. So the difference lies in the relative positioning of the views. You study these two charts, you will realize. But the nature of the views are exactly identical. You compare the front view of the first angle system with the front view of the third angle system, you will find there is no difference in the nature of the view. You compare this front view with this front view, you will find absolutely no difference as long as the object remains the same. So the object has indeed remained the same here. If you compare this top view with this top view, there will be no difference. If you compare this left-hand side view with this left-hand side view, they are exactly identical. Because the object is the same, how will their left-hand side view be different in the two systems? Similarly, if you compare the right-hand side view in the two systems, you will find no difference. The difference will lie in the relative placements of the views. So why are the relative placements of the views like this? That is what you need to understand. So let me explain that using a blank screen. Hopefully this time I will be able to do this in one shot. So let me go to let me use white screen. Okay. So let me explain the relative positioning of the views in the first angle system. Then we will take up third angle. Why the relative positioning of the views are like what we have seen just now in the first angle system? Let us try to understand that. So let us start with the vertical plane. So since we are studying first angle system, definition says object is located in the first quadrant. So we will draw only the first quadrant. We will not draw the other three quadrants. So we will draw only the first quadrant. So this is the VP, this is the horizontal plane. So the object is located somewhere here. You see where I am moving my pointer. The object is located somewhere here in the first quadrant, in front of VP and above H. So when you are looking at the object from the front, you are looking along the direction of this arrow, and you will get the front view of the object on the vertical plane. When you are looking at the object from the top, you are looking along the direction of this arrow. So you will get the top view of the object on the horizontal plane. Now, other than front view and top view, we have left-hand side view and right-hand side view. So both these views will be projected on planes which are called as profile planes. So one profile plane can be drawn here. So let me call this as PP1. Another profile plane can be drawn here. Let me call this as PP2. So when you are trying to obtain the left-hand side view of the object, you are looking at the object along this direction. Object is located somewhere here. So my question is, will the left-hand side view be projected on PP1 or on the profile plane PP2? Which is the correct profile plane on which the left-hand side view will be projected? How will you understand that? So for understanding that, you have to do some logical reasoning. So what is that? There are three things: observer, object, and plane of projection. You have to see what is the order in which these three things are appearing. So when you are drawing the front view, object is here in the first quadrant. Object is located somewhere here where I am circulating my pointer. Observer is located at infinity, at an infinite distance. This is where the observer is. Object is somewhere here, and plane of projection comes at the end. So when I am drawing the front view, observer comes first, followed by object, followed by plane of projection. So this is the sequence. Let me check whether this sequence is intact when we are drawing the top view. So when I am drawing the top view, observer is here at a theoretically infinite distance from the object, at the top of the object. Object is somewhere here in the first quadrant, and plane of projection, which is the horizontal plane, that comes at the very end. So again the sequence is observer followed by object followed by plane of projection. So since this same sequence is followed by front view and top view, this sequence has to be obeyed by the remaining views also. That is, left hand side view has to obey this sequence, and right hand side view also has to obey this same sequence. Observer followed by object, and at the end we will have the plane. So if you have to respect this sequence for the left hand side view, if this is the position of the observer and this is the position of the object, the plane of projection which comes after both observer and object, that is PP1. If you get the left hand side view of the object on PP2, then this sequence will change to observer, plane of projection, then object. So that cannot be allowed. That is why left hand side view will be obtained on profile plane 1. And if that is the case, then while obtaining the right hand side view, observer is here, then comes object, then comes plane of projection PP2, profile plane 2. So right hand side view will be projected on profile plane 2. So now we understand why each view is projected on that particular plane. Now the final thing that we have to do before submitting our solution, before presenting our solution to someone else, we have to bring all the views onto the same plane by rotating some of the planes. So what is the rule of rotation? Vertical plane will not rotate. Vertical plane will not rotate. So which planes can rotate? Only horizontal plane can rotate, and both the profile planes, they can rotate. So these are the planes which can rotate. So this part of the rule answers. This is the first part of the rule. Rule for what? Rule for rotation. Why do we need rotation of the planes? Because we want to bring all the views into the same plane. So the first part of the rule says, the first part of the rule answers the question, which planes can rotate? And the answer lies here. Vertical plane cannot rotate. So you can rotate horizontal plane through an angle of 90 degrees, bring it in alignment with the vertical plane. Similarly, you can rotate each one of the profile planes through an angle of 90 degrees and bring them in alignment with the vertical plane again. Now the second part of the rule talks about the direction of rotation. So the direction of rotation should be such that first and third quadrants will open out. What is meant by this? Opening out of a quadrant means the quadrant becoming bigger. So look at this situation. I am drawing only two planes. This is horizontal plane. This is vertical plane. This is first quadrant. This is third quadrant. This is second quadrant. This is fourth quadrant. Now, suppose I am rotating the horizontal plane. Vertical plane cannot rotate. It is my drawing sheet. That is my assumption. So when I am rotating the horizontal plane and trying to bring it in alignment with the vertical plane, there are two possible directions in which the horizontal plane can rotate. The horizontal plane can rotate in this direction, So when the horizontal plane rotates in this direction, this part of the horizontal plane comes down, the other part of the horizontal plane goes up, because this is one single plane. So if this part goes up, this part has to come down. But if I follow this direction of rotation, due to this rotation, as the plane rotates, the first quadrant will progressively keep getting smaller and smaller, and same thing will happen with the third quadrant. The quadrants which will increase in size will be second and fourth quadrants, but that is not what the rule says. The rule wants the first and third quadrants to get opened out due to rotation of the planes. So if I rotate the horizontal plane like this, as a consequence of this rotation, the first and third quadrants will get closed. When the rotation is complete to an angle of 90 degree, the angle in the first quadrant will vanish, and so will the angle in the third quadrant. So this direction of rotation is not correct. That is why I have to rotate the horizontal plane in this direction. So that when the horizontal plane comes to this position, the first quadrant is now slightly bigger than 90 degree. Similarly, the third quadrant is now slightly bigger than 90 degree. As the rotation continues, the first quadrant keeps becoming bigger and bigger. The third quadrant also keeps becoming bigger and bigger. And second and fourth quadrants keep getting smaller and smaller, and ultimately they will collapse to 0 degree. So this is how the planes should be rotated, so that first quadrant opens out as a consequence of rotation. Third quadrant also opens out as a consequence of rotation. So now coming to this figure, I have to rotate the horizontal plane and the two profile planes in such a direction that will allow the first quadrant to become bigger. So horizontal plane will rotate in this direction to an angle of 90 degree. And when that rotation is complete, it will come and lie below the vertical plane. So what will be the new position of the rotated horizontal plane? Let me show with a different color. The new position of the rotated horizontal plane, after the horizontal plane has rotated through 90 degree, it will take up this position. This is the new position of the rotated horizontal plane with the top view in it. So I think from this part of the discussion, you can understand why in the first angle system, front view is above the top view. Now let us see what happens for the two profile planes. The profile planes have to be rotated in a slightly different way. So if profile plane 1 rotates along the direction of the red arrow to an angle of 90 degree, when that rotation is complete, this will be the position taken up by profile plane 1 after rotation. So the left hand side view will be here. So you see left hand side view is on the right hand side of the front view. So on the right hand side of the front view, we have the left hand side view. And what will happen to the profile plane 2? The profile plane 2 has to be rotated in such a way that the first quadrant will open out. So profile plane 2 has to rotate like this. So once that rotation is complete through an angle of 90 degree, this will be the new position taken up by profile plane 2. So profile plane 2 after rotation will come and lie on the left hand side of the vertical plane. Profile plane 2 contains the right hand side view. So you see the right hand side view finally will lie on the left hand side of the front view. Right hand side view is lying on the left hand side of the front view. So I think I have been able to explain the relative positioning of the views in the first angle system. Let us repeat this discussion for the third angle system, and we will do it slightly faster this time. So now we are going to discuss the relative positioning of the views. What happened? Now let us discuss the relative positioning of the views in the third angle system. The third angle system is what we are trying to discuss. We are towards the end of the class, slightly delayed we are from the planned timing. So please wait for a few more minutes. We will close this class very soon. So let us do the discussion for the third angle system. So when we are talking about third angle system, we are starting with the basic assumption that the object is located in the third quadrant. So we will draw only the third quadrant. We will not draw the other quadrants. We will draw only the third quadrant. So we will draw that part of the horizontal plane and that part of the vertical plane which contains the third quadrant. So this is that part of the vertical plane and this is that part of the horizontal plane which is containing the third quadrant here. This is the third quadrant. So object is located here, somewhere here. Now when you are looking at the object from the front view of the object will be projected on this plane. When you are looking at the object from the top view of the object will be projected on this horizontal plane. Now for side views, you have to first construct the possible profile planes. Let me call this as profile plane 1 and let me call this as profile plane 2. Okay. Now for left hand side view, we have to look at the object along this direction. And for right hand side view, we have to look at the object along this direction. So this is for front, this is for top, and these two are for left hand side view and right hand side view. Now again, logically, we have to understand which of these two profile planes will contain the left hand side view and which one will contain the right hand side view. So again, let us try to see how observer, object, and plane of projection are appearing. What is the sequence in which these three things are appearing? So let us start from the front view. When we are trying to obtain the front view, observer is here, object is somewhere here in the third quadrant within this box. And plane of projection, that is the vertical plane, is coming between the observer and the object. Object is inside this box. Plane of projection is coming between the observer and the object. So now the sequence is no longer observer, object, plane of projection. In first angle system, the sequence was observer followed by object followed by plane of projection. In the third angle system, this is no longer the sequence. The sequence becomes observer, plane of projection, and finally we have the object. So if this sequence has to be respected by the left hand side view, then left hand side view should be projected on this profile plane and right hand side view will be projected on this profile plane. Now one question might appear in your minds at this point. You may say that if the plane is coming between the observer and the object, then how is the observer able to see the object? This is a very logical question. The answer to that is, in the third angle system, we make an assumption that the planes of projection are opaque in nature. Sorry, the planes of projection are transparent in nature. This is an assumption that we make about the planes of projection in the third angle system. In the first angle system, we consider the planes of projection as opaque. In the third angle system, we assume that the planes of projection are transparent, so that although the plane of projection is appearing between the observer and the observer can still see through the plane and is able to view the object. So now we have obtained the plane, the projected views on the respective planes of projection. Now we have to do the rotation of the planes. So which planes will rotate? Again, horizontal plane will rotate, profile plane 1 will rotate, profile plane 2 will rotate through an angle of 90 degree, and after rotation they will align with the vertical plane. What is the direction of rotation? The direction of rotation should be such that now the third quadrant should become bigger. Third quadrant should open out. So in order to allow the third quadrant to get opened out, the horizontal plane should rotate in this direction. And once that rotation is complete through an angle of 90 degree, this will be the final position of the horizontal plane. So the rotated position of the horizontal plane is above the vertical plane. So top view will be above the front view in the third angle system. Top view will be above the front view in the third angle system. In the first angle system, front view was above and top view was below first angle. In the third angle system, top view is above and front view is below. Now we have to rotate the two profile planes to get a feel of the final locations of the side views. So to open out the third quadrant, profile plane 1, which contains the left hand side view, that should rotate like this. And after that rotation is complete to an angle of 90 degree, this will be the new position of profile plane 1. So left hand side view is lying on the left hand side of the front view. So left hand side view is lying on the left hand side of the front view. What was the location of the left hand side view in the first angle system? On the right hand side of the front view. Similarly, the profile plane 2, which is containing the right hand side view, it should rotate in this direction to allow the third quadrant to get opened out. So once the rotation of the profile plane 2 is complete through an angle of 90 degree, this will be the new position of profile plane 2 with the right hand side view in it. So you see, right hand side view in the final solution is on the right hand side of the front view, which was not the case in the first angle system. In the first angle system, right hand side view was lying on the left hand side of the front. So if you compare these two results, you will understand where exactly the difference lies between the execution of orthographic projection drawings following the first angle system and the execution of the same thing following the third angle system. So this is the consequence of positioning the object in the first quadrant, this kind of relative positioning of the views. And this is the consequence of positioning the object in the third quadrant, this kind of relative positioning of the views. The nature of the views will not be different, but the relative positioning of the views will be different. Now you see, when two orthographic views are lying in a column vertically, one below the other, then these two views have to be front view and top view. Which one is front view, which one is top view? That will depend on whether we are following first angle system or third angle system. But when two views are given to you like this, view 1 and view 2, when the two views are arranged in a column vertically, then these two views can be combination of front view and top view. None of them can be side view. Because on top and below any side view, can you find any other view? The answer is no. Similarly, if two views are given side by side, view 1, view 2, if two views are given like this, then none of them can be the top view, because on two sides of the top view in both the systems you see, on two sides of the top view there is no other view. So when two views are placed side by side, they have to be, one of them has to be the front view, the other has to be one of the side views. So which one is the front view, which one is one of the side views, which side view is that, all those answers we can give only after we know about the system of projection. But without that information, at least we can make a decision about the identity of these two orthographic views which are placed side by side. We can say that one of them is the front view, the other one is one of the two side views, if the views are given like this side by side. And if the views are given like this vertically, one below other, arranged in a column, then one of them has to be the front view, the other one is the top view. And if they are given in a row, arranged horizontally with respect to one another, then one of them is the side view, one of them is the front view, the other one is one of the two side views. Now, you may do your work, that is, draw the orthographic projections of an object according to the first angle system. You can do your work, someone else can do his work according to the third angle system. Now there is another person who is looking at your drawing sheet. and trying to understand what you have drawn. How will that person know which system of projection you have followed? So you have to indicate clearly in your drawing sheet somewhere about the system of projection that you have followed. Whether you have followed the first angle system or whether you have followed the third angle system, you have to clearly mention that. So for that, we have a cell in our title block where we write something about system of projection. We put some information about system of projection. So in the earlier drawing sheets which you have done on line types, lettering and dimensioning and on scale, where system of projection was an irrelevant concept, you did not write anything meaningful in that cell. You just wrote these 3 words. But from now on, whenever you will be doing any drawing on projection, then you have to explicitly mention whether you have followed the first angle system of projection or whether you have followed the third angle system of projection in that cell of the title block. So how will you indicate? Will you write first angle system or third angle system in words? The answer is no. There is a symbol, there is a standard symbol called as BIS symbol. BIS stands for Bureau of Indian Standards. So BIS has introduced a standard symbol, which is the symbol for first angle system of projection. Similarly, there is a BIS symbol, which is a standard symbol for third angle system of projection. So if you are following third angle system of projection, you have to draw the corresponding BIS symbol. And if you are following the first angle system of projection, you have to draw the corresponding BIS symbol in that cell of the title block, where till now we have written system of projection. So we will end the class by looking at the BIS symbol for the 2 systems of projection. So you see, this is the BIS symbol for the 2 systems of projection. And you can see that by swapping the 2 views, you can go from one system to the other system. So this is the BIS symbol for the first angle system of projection. This is the BIS symbol for the third angle system of projection. So what is the meaning of this symbol? There must be some hidden pattern inside this symbol. I am trying to explain that pattern. See, this is a cone. All of you know this. Now imagine that you are cutting this cone by an imaginary cutting plane, which is horizontal. And you are removing this top part. You are getting rid of this top part. So whatever is remaining from the original cone, that leftover portion of the cone will look like this. This geometry is called as frustum of a cone. Frustum of cone. This kind of geometry. Now, if you rotate this frustum of a cone through an angle of 90 degrees, now it will take this form. Now, if you look at this from the front, you will see something like this. This is the front view of a frustum of a cone whose axis is horizontal. And if you look at this frustum of a cone from the left hand side, this is what you will see. So this is the left hand side view. Now, according to the first angle system, front view has top view below it, left hand side view on the right hand side of it, and right hand side view on the left hand side of it. So you see, front view and left hand side view, they are located like this. Front view is located to the right and left hand side view is located to the left. So this symbol is consistent with this result. So this is the symbol for the first angle system. Now in the third angle system, what is the relative positioning of these 2 views? Let me draw the entire chart. Front view is below the top view and left hand side view is on the left hand side of the front view. Right hand side view is on the right hand side of the front view. So in the third angle system, the left hand side view and the front view, their positions are exactly opposite of what their positions were in the first angle system. That is why when you are moving to the symbol for third angle system of projection, you have to simply exchange the positions of these 2 views to get the modified symbol for the third angle system of projection. So in a nutshell, if you are doing your work according to the third angle system of projection, this is the symbol which you have to draw in that shell of the title block, where till now you have written system of projection. And if you are doing your work according to the first angle system of projection, this is the symbol which you have to draw in the relevant cell of the title block. Now, in our practical class, we will solve two types of problems. We will start with isometric view of an object and draw the orthographic views. Then we will start with orthographic views of an object and draw the isometric view. But due to lack of time in our practical class, we will solve only one example. But for your practice purpose, you have plenty of examples in these upcoming slides. The slides following this one, they contain plenty of examples of isometric views of an object and orthographic views of the same object. So those examples are present here in your study materials. Please go through these examples and try to understand the relation between each isometric view and the corresponding orthographic views. See to it whether you are able to develop the orthographic views from the given isometric view and whether you are able to do the reverse exercise. So if these orthographic views are given to you, you should be able to develop this isometric view yourself. And if this isometric view is given to you, you should be able to develop the orthographic views yourself. So if you face any problem in this part, trying to convert isometric to orthographic or orthographic to isometric, please meet me in your free time. We will have a face-to-face discussion. Okay. So thank you for attending this class. So good night, all of you. If you have any questions, you can post them in my personal WhatsApp, or you can share them with me when we meet in the physical classroom. Okay, thank you. So you can leave the meeting one by one.